Yeah. So if you want to find the like 3 to a really large power or any number to a really large power, using the for loop is going to take a long time to do that task. It's very slow, it's inefficient, and there's a better way to do that if you want to find something to a really large power. And we can use the fact that if we know, if we want to find 3 to the 8, for example, if we know what 3 to the 4 is, all we have to do is take 3 to the 4 and square it, and that's equal to 3 to the 8th. And similarly, 3 squared, if we know what 3 squared is and we square that, we get 3 to the 4. And if we know what 3 to the 1 is, which is just 3, if we square that, we're going to get 3 squared. So you can see that using this process of squaring whatever number we get each time, we only require 3 steps to get to 8. Whereas if we had just gone one by one and multiplied 3 8 times, that would have required 8 steps. So binary exponentiation uses this fact that we can take this exponent that may be really, really huge, and we can keep splitting it in half each time and finding that smaller number. So instead of finding 3 to the 8th by 8 by multiplying 3 8 times, we can keep splitting it in half to find the smaller numbers. And now if we have a power that's not divisible by 2 or is not a power of 2, the way that that would work is we can we know that we can break this 11 into powers of 2 by having 1 plus 2 plus 8. We know that this 11 can be broken up into 3 chunks, one chunk of 1, another chunk of 2, and another chunk of 8, which means that 3 to the 11 is equal to 3 to the 1 times 3 to the 2 times 3 to the 8, which again means that if we're able to calculate each of these parts, then we can easily calculate 3 to the 11th. And the runtime of binary exponentiation, as the name suggests, it's going to be logarithmic. It's going to be log base 2, whatever your exponent is. And this is a lot faster than just regular n. Because as I said before, if you want to calculate 3 to the 100 trillion mod some smaller number, that can be done really quickly in comparison to actually having a for loop go that many times, in which case you may run into your computer may crash and other problems like that may arise. So yes, that's what we're going to cover now. And there's a couple of ways to do it. There's an iterative way, there's a recursive way. Before we do that, I just want to make sure you guys are comfortable with some bitwise operators. So I know we haven't covered these in the meeting. I'm not sure if they're covered in like CS3 or something, but this is the AND operator. So this is bitwise and this is a bitwise left shift. All this basically means is that we're taking at one left shift I bits basically is equal to 2 to the I. That's all this means. This over here is just equal to 2 to the I. And if you're not familiar with the AND operator, it basically compares the bits in each position. And if they're the same, then that's a one. If they're the same and they're 1, then that's a 1. So let's say I have these two numbers here, and these numbers are in binary. So maybe this is equal to like, this is just a random guess, but maybe it's equal to 89 or something like that. But we represented it over here in binary. And let's say we have this second number over here. If we take both of them and we AND them together, it's going to be 1 where both of them are 1. So it's going to be 1, then 0, then 0, then 0, then 1 over here because they're both 1 in this position, and then 0, and then 1. And the reason I'm bringing this up is because if you want to find what powers of 2 a number is made of, like test over here, we can easily do that using this process over here. We can shift I, we can shift I, we can multiply 1 by a power, by 2 to the power of I, and we can take that number and AND it with whatever number we're testing for. So if I run this example over here with test, you're going to see that it prints out 2 and 3 because 12 is equal to 2 squared plus 2 cubed. And that's what it's printed out. It's printed out these exponents over here. And the way that this works is because 1 to the I is a power of 2, if we take, for example, 2 squared and we represent in binary, it's going to look like 1, 0, 0. And if you look at 12 in binary, it's going to be 1, 1, 0, 0. So now when we add these two numbers together, we're going to get 0, 1, 0, 0, which is equal to 4. And because 4 is greater than 0, because they actually share something in common in this position, in order for it to be greater than 0, then we know that 2 to the power of I is going to be a power of 2 that can go into the sum of 12. And if you don't understand that, that's fine. Just know that this is a fancy way to find what powers of 2 are can be added together to make 12. So 2 squared can be 2 squared and 2 cubed can be added to make 12. Now that we have that out of the way, what we're going to do is we're going to have, let's say for this example, we want to find, um, let's say we want to have 3 to the power of 6. We'll do something simple. And this is equal to 729. So the way that we would do this is we would have an answer variable that starts off at 1. And then we would have a pow variable that starts off at 1. And this pow variable basically tells us 3 to the power of some power of 2. So first what we're going to do is we're going to check if if 2 to the I is something that can go into A to make it, like if 2 to the I is something that can be added to other powers of 2 to make A, I mean, to make B is the exponent. So B is the exponent. Then what we're going to do is we're going to multiply our answer by pow. Why is this giving me an error? You've got to wrap it in parentheses. And then what we're going to do in each phase is multiply pow by itself. And let's just test if this works, and I'll explain it once more. Okay, printed 1, which is not what we wanted. So let's debug it together. So yes, this is correct. 2 to the 1 plus 2 to the 2. 2 to the 1 plus 2 to the 2 equals 6. So that part's correct. Pow time. Oh, no. Okay, no, wait. Pow times equals pow. I think pow should start off at A. Let me just check this. Okay, there, that worked. Yes, you can see it found 3 to the 6th. And just to make sure that this works, we'll try 7 as well. And it prints out 2187. Yes, I'll go over the code once more to explain what it actually does. So A is we're trying to find A to the B really fast. And the reason for this is because B can be this humongous number, and we'll test it soon with a really large number, but it can be a really large number, and we want to calculate this product really fast. So that's what we're trying to do. We're trying to find A to the B. What this power over here is going to keep track of is it's going to keep track of 3 to the some power of 2. So first pow, when we go through our loop, pow will be A initially, be 3. And then after 3, it will become 3 times 3, which is 9. So first will be 3. And then it'll be 3 times 3, which is 9. And then it'll be 9 times 9, which is 81. And the reason it's going to be this is because you can see here we're multiplying it by itself. So I hope everybody understands this part. We're just taking pow, and each time we go through the loop, we're multiplying it by itself. So it starts off at 3, then we multiply it by itself, it becomes 9. We multiply by itself, and it becomes 81. And what this basically is this is 3 to the power of 2 to the 2. This is 3 to the power of 2 to the 1. This is 3 to the power of 2 to the 0. And the reason we're computing pow is because remember what we said about the exponent was that if we want to find 3 to the 6, this is equal to 3 to the 2 plus 3 to the 4. So that's why we're increasing pow as we go. Pow is going to be each of these over here. And then if this 2 is used to make the sum of 6, we're going to multiply our answer by pow. So for example, 3 to the 6th is made up of 3 to the 2. That should be a multiplication sign. 3 to the 2 times 3 to the 4. So if we know what 3 to the 2 to the 1 is, which is basically 9, we're going to multiply by our answer. And then and the next time we go through our loop, pow is going to be 3 to the 2 squared. So it's going to be 3 to the 4. And we're going to multiply that again by our answer because 3 to the 6 is made up of 3 to the 2 times 3 to the 4. And once again, all this does is check if 2 to the I um, is one of those exponents that adds to 6. So all it's checking is 2 to the 0 something that adds up to 6 over here? And no, 2 to the 0 is 1. We don't see 1 over here. We only see 2 and 4. And then I will become 1. And it says, is 2 to the 1 something that we see over here? And yeah, we have 2 to the 1 right over here. Because 2 to the 1 is over here, we're going to multiply 9 to our answer. And then
Can
in
I
this
ask
case,
you
2,
a question?
yeah.
On line 13, what is that hard coded for about? Look, what is that
Um,
for?
it, yeah, I mean, that's basically how many powers of 2. Well, so what you want to do is you could take this log base 2 and then seal it, and then you can go up to that number. 4 is just a arbitrary number they can go up to. It's just going to check if 2 to the I can go into the b exponent over here. If we chose something like 1, it's going to give us the wrong answer because it didn't loop enough times. So if I run this with 1, you can see it just prints out 1. Um, because the largest power of 2 needed to add up to 6 is going to be 4. If we use 3, if we use less than equal to 2, this is going to give us the correct answer for 729. But the second I increase this to something like 15, which requires a larger power of 2, 15 is made up of 1 plus 2 plus 4 plus 8, you can see it gives us the wrong answer. So for 15, we'd have to go up to like less than equal to 4 or less than equal to 3, something like that. So you can see now I'll give you the correct answer. Yeah, that's what it is though. You could just say math.log. Is there no log 2 in C++? There is. You could just, or you could have a while loop to keep on increasing a variable to find how many times, find the smallest power of 2 that is greater than or equal to b. But that's basically what it is. It's how many, what's the largest exponent of 2, what needed to add up to b. That was a good question. I don't know what else to explain about this, but if there's something that you don't understand, you can ask more questions. And the reason I wanted to cover this is because there's a problem on the contest that I wrote. What is the contest called? So from our PESH contest, there's a problem called big addition. And this problem was intended to be solved with binary exponentiation. There's some people who kind of cheated and used big integer in Java. And apparently the Python function has, the Python power function has a modulo option. I didn't know about that. I wanted people to code it with binary exponentiation. But basically in this problem, how do I see this problem? Come on.
Can
Basically
you
in this problem,
preview
you had some really large numbers that you had to add up.
the challenge,
And
maybe?
because these numbers were so large, you could not just add them up directly. You had to find a mod, you had to find their sum mod some other number. So let's take a look at that problem. Here it is. At a 40.91% success rate. Yeah, so you're pretty much given this, you have you have pairs of numbers on the second line, and this represents over here 2 to the 5th, this represents 2 to the 4th, and you have to find the sum of all of these numbers, mod 10 to the 9th plus 7, 10 to the 9 plus 7. So this makes it seem easy. Maybe you just use a for loop to calculate 2 to the 5, then you use a for loop to calculate 2 to the 4, and you add them together. But the problem is the exponent can go up to 10 to the 9th. It can go up to a billion. It can go up to a billion. A can go up to a million, and you can have as many as 100,000 of these numbers. So using a for loop is going to take too long. Number one, because a billion is super huge, but on top of that, you also have really large numbers to deal with. So the intended solution for this problem was to use binary exponentiation, pretty much exactly what we used over here, except instead of, in addition to saying ants times equals mod, ants times equals pause, pow, we'd also mod it by 10 to the 9 plus 7, because this can get really big. So that's what mod does. It basically takes the remainder of the product. And that was the solution for big addition using modular exponentiation. So this is a fun problem to tackle by yourself. I'll copy and paste the
And
code
just one thing to add,
to the chat.
like whenever,
Yeah, Kanish.
yeah, I was just gonna add that. Um, wait, is it? It's fine if you modulo like in the middle rather than the end, right?
Yeah, you kind of have to mod while you're doing the multiplication
No, okay.
addition. Yeah, so now that you guys know binary exponentiation or have an idea of how it works, I'd recommend playing around with the code I just pasted into the chat. If you don't fully understand the code, the best thing to do is to have print statements throughout the code. So maybe you don't understand what this does over here. So just like copy this, write a print statement, paste it, and just print it out and see what happens when you run this bit of code over here. And you can see when we run this bit of code, it's going to print all the powers of 2 needed to add up to 15. So you can see over here, 1 plus 2 plus 4 plus 8 is needed to add up to 15. Let's see what's needed to add up to 115, for example. So this is just a random number. I should make this bigger. So if I run this now, we can see that 1, 2, 16, 32, and 64 are the powers of 2 that add up to 115. So when you play around with the code a bit, you'll just have a better understanding of what it does and how it works. And when you feel confident about how that binary exponentiation works, it's pretty much just copy and paste to solve this problem with a few modifications. But this would definitely be something good to practice. So I'll